In this video, we're going to be looking at part 2 of topic 1E, formula, equations and calculations, and we'll be focusing on the double content as part of the IGCSE chemistry course from Edexcel. So we're going to be looking at how to calculate reacting masses using experimental data and our chemical equations. This will then lead us into determining percentage yield. We'll then look at how to figure out the formula of simple compounds experimentally, and then using that information to help us figure out empirical formula and molecular formula. And then lastly, how to determine the formula of a metal oxide either by combustion or by reduction. So what do we actually mean by a chemical formula? Well, a chemical formula tells us how many atoms are present in a compound. So for example, we've got SO2, which is sulfur dioxide, and that tells us that there are 2 oxygens. So this subscript tells us the number of that atom, and if there's no subscript, it means it must be 1, so there is 1 sulfur. And in terms of the chemical formula that we're going to be looking at, there are 2 that we need to understand what they mean and be able to figure out for a particular substance. And these are known as empirical and molecular formula. So empirical formula is the simplest whole number ratio of the atoms present. So it is about finding the ratio that doesn't have any multiples. So for example, if you had x2, y4, that would not be an empirical formula because you can make a simpler ratio of 2 to 4. That empirical formula would be x, y2. Because they would be in a 1 to 2 ratio. The 2 and the 4 are simply multiples of that ratio. Now, molecular formula shows the actual number of atoms that are present in a covalent compound or the formula unit of an ionic compound. So remember, for covalent, it is the actual number, and this will be reviewed when you do bonding as well, but you've probably come across this before, whereas ionic, it is the ratio of the atoms in the lattice. So you may find that molecular formula and empirical formula are the same for certain substances, but sometimes they are different. So for example, if we have a molecular formula of C4H8, which means I have 4 carbons and 8 hydrogens, that will have an empirical formula of CH2. Because its simplest whole number ratio is a 1 to 2 ratio. But in actual reality, it has 4 carbons and 8 hydrogens. So what we should be able to do is we should be able to, from a specific set of data, calculate an empirical formula. And the way that you do this is the same every time. You'll be given all of the information that you need to answer the question in the formula, and you will set up a table that looks like this. So you will be told the different elements, for example, potassium, manganese, and oxygen, and you will be told a mass, or sometimes you're told a percentage. Okay, but regardless of what one you have, you would do this process in the same way. The mass is obviously different from the percentage in terms of what they mean, but the way the calculation is carried out is the same. The first thing that we then do is we determine the relative atomic mass of each of these. And we can lift this information straight from the periodic table. And remember, you will always have access to a periodic table in your exam. You're not expected to memorise it, and it will generally be at the back of your exam paper. So when we look up the relative atomic mass for each of these, we find that potassium is 39, manganese is 55, and oxygen is 16. The next step is then to apply our mole triangle. So from part 1 of this, you've learned that the mole triangle is mass, moles, MR. Now the MR could also be AR, your atomic mass, rather than your molecular mass. It's the same thing in this case. We apply it in the same way. So we want to work out our number of moles for each of these. So I'm going to start with 0.78 divided by 39, and that gives me 0.02. For the manganese, I do 1.10 divided by 55, and that also gives me 0.02. For the oxygen, I would do 1.28 divided by 16, and that gives me 0.08. Now what we do for the next step is figure out the whole number ratio, and we do this by dividing by the smallest number of moles. So we look at the values that we have, and we can see for each out of the three of them, 0.02 is the smallest. So we divide every number of moles by 0.02. So I have 0.02 divided by 0.02, giving me an answer of 1. That's the same for the manganese. And then for the oxygen, it's 0.08 divided by 0.02, and that gives me an answer of 4. These are the numbers that I then use for my ratio. I have a 1:1:4 ratio. So my answer for my empirical formula is going to be KMnO4. Now we can calculate the empirical formula for a substance in lots of different ways. We can use that information that would be given in a question, or if we have a specific oxide, we can determine it using combustion analysis. And combustion analysis is essentially we burn the substance and we weigh it to figure out its mass, and we then determine how much oxygen has been lost. So we weigh the sample into a crucible, which is essentially a small ceramic pot, and we have a lid on it. We weigh the sample and then we heat it. Then we weigh it again and we heat it. And we continue this heating and weighing until we reach a constant mass. And once we reach a constant mass, it means that we are not going to be losing any more oxygen. So all of the oxygen will be lost once it's heated to a constant mass, and then from that information we can determine the empirical formula, because we would be able to weigh what we started with and then what we ended with. And once we know what has been lost in terms of oxygen, what's left over must be our metal. We can also figure out an empirical formula by looking at water of crystallization. So you may have seen this previously when you were looking at formula, where you saw a salt with a dot and then some water attached to it. Now that water is known as water of crystallization, and it's not fully bonded to each of the atoms, it's just simply attracted to it. Now you don't need to know how it's attracted or why it's not bonded, you simply have to know that it exists. And what we can do is we can heat a salt to drive off this water of crystallization and leave what's known as the anhydrous salt. And this is actually something you will touch on again in topic 2H, chemical tests, when you're looking at the test for water. Once we've driven off the water, what we can do is we can find the ratio of how much salt was left over at the end to how much water was removed. Very similar to the way that we have the oxygen. So we weigh the salt in our crucible, we then heat it and weigh it again, and again we heat to a constant mass. Anytime you have a question like this, you should always use that term. We're heating to a constant mass. Once we're at a constant mass, we've lost all of the water, and we can determine how many moles of water were attached, and then we can figure out what our formula is. So once we have the empirical formula using the method that we've just looked at, we can then determine the molecular formula, provided we have the MR of the compound. Remember, MR is your relative formula mass. The empirical formula is your simplest ratio, whereas the molecular formula is the actual number of atoms. So for example, if we have C4H8, that would be our molecular formula, and the simplest whole number ratio, rather than it being 4:8, would be 1:2. So my empirical formula would be CH2. So once we have the empirical formula, we can determine the MR of that formula, and we then take the MR of the molecule and then divide that by the empirical formula, and then that finds a ratio, and we then multiply that. So if we have C2H5, we know that that has an MR of 29 because it would be 5 times 1 is 5 and 2 times 12 is 24. Add those together and that's 29. We're told that the MR of the molecule is 58. So we do a division, we do 58 divided by 29, and that gives us a value of 2. And that means we then multiply our empirical formula of C2H5 times 2 to give us a molecular formula of C4H10. And you would do this for any molecular and empirical formula you have. So you determine the MR of the empirical formula, divide the MR of the molecule by the MR of the empirical, and then multiply your subscripts by whatever that ratio number is to determine your molecular formula. So moving on, we're going to look now at reacting masses or calculations from balanced equations. If we have a balanced chemical equation, we can determine the number of moles or the mass of each reactant that we use or each product that we form. And regardless of whether we're looking at reactants or products, there's a foolproof method to follow through and get your answer to these questions. And the method involves 4 steps. So the first step is to write the balanced chemical equation. Now, sometimes that is given in the exam. And the reason that's sometimes given in the exam is if you get the balanced chemical equation wrong, your entire answer will be wrong even if you follow the correct method. So some exam bodies think that that's unfair, and they give you the balanced chemical equation you'll need so that any errors or marks lost are simply due to calculations rather than something that you've previously done. But it does just depend on the year and it depends on the paper. So once we have our chemical equation, we then determine the number of moles of the known substance. And that means from the information that is given in the question. So in the question, we will be told a mass or a moles of one of our specific substances in our equation. Then, once we know that, we use a mole ratio to determine the number of moles of the unknown substance. So this is the substance in the question that we want to know about. So that you may be asked, calculate the number of moles of oxygen. So our unknown substance would therefore be oxygen. Once we then have that mole ratio, we can then determine the mass of that substance. So what the best thing to do is to put this into practice. So we want to calculate the number of moles of calcium oxide that is formed when calcium carbonate, when we have 25 grams, decomposes. So step 1, write the chemical equation. Well, in this case, we start with calcium carbonate, which is CaCO3, and that's a solid, and it decomposes into calcium oxide, which is also a solid, plus carbon dioxide, which is CO2, and that's a gas. We can check our balancing on both the right and left. I have 1 calcium. I have 1 carbon on the left, 1 carbon on the right, 3 oxygens on the left and 3 oxygens on the right. So that is now balanced. So step 2, calculate the moles of the known substance. So remember our triangle is mass, moles, MR. So to calculate the number of moles, we need the mass and we also need our MR. So for the MR, we have to do that first. So we have CaCO3, and that would be 3 times 16 is 48, 1 times 12 is 12, 1 times 40 is 40, giving us an MR of 100. So our number of moles is mass over MR, which is 25 over 100, and that is 0.25 moles of calcium carbonate. Step 3 is now to look at the mole ratio. So what I advise doing is look through the question and identify the two things that you're interested in. We are interested in calcium oxide and calcium carbonate. This tells me I'm only interested in these two things and I can ignore the carbon dioxide. So to determine the mole ratio, we look at the coefficient. Now both of these have no coefficient, which means they are in a 1-to-1 ratio. Therefore, if I have 0.25 moles of calcium carbonate, I'm going to make 0.25 moles of calcium oxide because they're in a 1-to-1 ratio. So then my final step, step 4, is to calculate the mass of the unknown substance. So we also need an MR again. So for CaO, we've got 16 for the oxygen plus 40, giving us an MR of 56. So our mass is going to be the number of moles times the MR. So 0.25 times the MR of 56, giving us a mass of 14 grams. So this means that when I decompose 25 grams of calcium carbonate, I will make 14 grams of calcium oxide. Let's look at another example. This time we have 32 grams of methane being burned and we want to know how much water is being formed. Now, you may not have covered the organic topic yet. It depends on the order of the units that your teacher chooses to do. So don't worry too much if you don't know this equation. You will learn it later. If we have methane for step 1, for our balanced chemical equation is CH4, and that's a gas. We burn it in oxygen, which is also a gas. And every hydrocarbon is going to form carbon dioxide plus water. When we're discussing burning, unless it says otherwise, we will assume that it is always complete combustion. So of course we're going to have to balance this. So we have 1 carbon on the left and 1 carbon on the right. We have 4 hydrogens on the left, so we need 2 more on the right. And that gives me then 4 oxygens. So then that should be a 2 in front of the oxygen. We're then going to determine the number of moles of our known substance. So that's our CH4. Of course, we need our MR. So remember, we have mass, moles, MR. I would suggest when you go into an exam that you write that equation down somewhere, perhaps on your periodic table, just so that you can refer back to it each time and not have to worry about it all throughout the exam. But for hydrogen, we've got 4 times 1 is 4, and then 1 times 12 is 12, which gives us 16. So my number of moles is mass over MR, so I have 32 divided by 16, which gives me 2 moles of methane. Step 3 is the mole ratio. So we are looking at methane, which is the CH4, and water, which is the 2H2O. So we can ignore everything else. So our mole ratio is 1-to-2. Therefore, if I have 2 moles of CH4, I need 2 times that for the water. So I will have 4 moles of water. And then step 4, to calculate my mass, is N times MR, and H2O is going to be 16 plus 2, so it has an MR of 18. So I have 4 moles times an MR of 18, giving me 72 grams. So again, what does this actually mean? Well, it means that when we burn 32 grams of methane, we will form 72 grams of water. The next part of the calculations topic is looking at the percentage yield. And this is essentially looking at the percent ratio of what you actually make as a product versus what you should theoretically make. So when you have your theoretical, that is from your calculation from balanced equation. So using the method that we just practiced a few minutes ago. Whereas the actual yield is when you carry out the experiment, what do you actually make? And most of the time you will be told this in the question, unless this is the thing that you're being asked to determine. But 9 times out of 10, you will be told what the actual yield is. So we're looking at how much we actually make versus how much you should have made, and we express this in terms of a percentage, and this is the equation that we use. So you are not given this in the exam, you do need to remember it, so please make sure that you do commit this to memory. But it's very similar to any other percentage, like in a test. You would always do what you actually got, so for example 60 marks, divided by what you could have got, which would be the total, i.e. 100 marks, and then you can determine the percentage. So an example that we have here is a student reacting 2.4 grams of copper oxide with hot sulfuric acid, and she made 5.21 grams of copper sulfate crystals. And we've got two equations here to help us determine the percentage yield. So the first thing that we're going to have to do is we need to calculate the theoretical yield. So that's our steps. Now we already have the balanced chemical equation, so we don't need to do that. We first have to then jump to step 2. So we're going to work out the number of moles, which is our mass divided by MR, of our copper oxide, because that's the thing that was reacting, and we're told we use 2.4 of that. So we use 2.4, and the MR for copper oxide, which is CuO, is 16 plus 63.5, giving you an MR of 79.5. So our number of moles is 0.0302. The third step looks at our mole ratio. Now we are using the copper oxide, but we are making these hydrated crystals. So we need to look at the ratio over the two equations. So between the copper and oxide and the copper sulfate and the first equation, it's a 1-to-1 ratio. Then between the copper sulfate and the second ratio, and the second equation with the hydrated, again, it's a 1-to-1 ratio. That means 1 mole of copper oxide will give me 1 mole of the hydrated copper sulfate. So my mole ratio is 1-to-1. Therefore, I have 0.0302 moles of my CuSO4.5H2O. From that, we can then determine our mass. So the mass is the number of moles times the MR. So that's 0.0302 times the MR, which you would be able to calculate using our method that we've used multiple times, is 249.5, giving you a theoretical yield of 7.53 grams. Now to determine our percentage yield, we do the actual divided by the theoretical times 100. So the actual we get from the question. We have 5.21 divided by our theoretical, where we've just worked out, is 7.53 times 100, and that gives you a percentage yield of 69.2%. Now the last thing that we need to be able to do is something known as an excess calculation. And this is something that you will cover again at A level, but you do need to understand the concept for GCSE. Now, usually in experiments, reagents are mixed in the correct proportions. So if we need 1 mole to 2 moles, they are mixed in that correct proportion. But sometimes one particular reactant may be in excess. What does that mean? Well, if a reagent is in excess, it means that we have way more than what we actually need to in order to react. And then the other reactant is known as the limiting reagent. So you will either have a limiting reagent or an excess reagent. And you may be asked to calculate which reagent is in excess. And this involves using our mole triangle and looking at our mole ratios. And again, you can use a table to show you how to do this. And if you follow the steps through the table each time, you will always get the right answer, provided you don't make any mistakes on your calculator. So we have 3.2 grams of copper reacting with 0.4 moles of nitric acid, and we want to determine which reagent is in excess. Now, they've given us the equation, so we don't need to write that out. Typically, for an excess calculation, you'll be given the equation just to make sure that you use the right ratios. So we are only interested in the copper and the nitric acid. We actually don't care about the products. They are not the purpose of this calculation. We are only interested in the reactants. So if we take the copper and the nitric acid and we look at firstly their mole ratio. So we have a 1 to 4 ratio. 1 mole of copper to 4 moles of nitric acid. Then I use the information from the question to determine how many moles I have. So for the nitric acid, it's quite simple. It tells us that we're using 0.4 moles. Whereas for the copper, it's 3.2 divided by the relative atomic mass, which is 63.5, which gives me 0.05 moles. And then now what we can do is we can look at what we have versus what we need. So what we have is simply just the moles that we've just calculated. So 0.05 to 0.40. And when we say need, we are looking at if I want to use up all of one of my reactants, how much of the other one do I need? So for example, if I want to use all of my 0.05 moles of copper, because they are in a 1 to 4 ratio, I need 4 times that. So I need 0.05 times 4, which is 0.20. And now I compare what I need to what I have. And what I can see is that 0.4 is of course larger than 0.2. So I have more of the one that I need. So that means that the nitric acid is in excess and the copper is our limiting reagent. If we look at another example, we've got 28 grams of carbon monoxide reacting with 0.6 moles of Fe2O3. Again, we want to determine which one is in excess. So our mole ratio of our reactants is 1 to 3. Remember, we're not interested in those products. So how many moles of each do we have? Well, we're told that we have 0.6 moles of the Fe2O3, and we need to determine for the carbon monoxide. So I have 28, and my MR is also 28, so I have 1 mole of the carbon monoxide. So again, if I want to look at what I have, that's those numbers, versus what I need. Well, let's say I want to use all of my iron oxide, which is 0.6. How much will I need? Well, they're in a 1 to 3 ratio, so I would need 0.6 times 3, which would be 1.8 moles. I look and I do my comparison, and we can see 1.8 is less than 1.0 is less than 1.8, meaning I don't have enough of the carbon monoxide to react all of the iron oxide. That must mean that this is the limiting reagent, whereas the iron oxide is in excess. Now we're going to finish off by looking at some past paper questions, and we'll look at a number of different types of question that could come up that will cover everything that we've looked at in this video. So the equation for the thermal decomposition of copper carbonate is CuCO3, giving us CuO and carbon dioxide. The student is investigating this decomposition using this apparatus and method. So we are weighing the crucible and our copper carbonate, we're heating it and weighing it again, heating it, weighing it again, and continuing to do this and recording for each of our experiments what our masses are. And you can see that we have this table at the bottom here. So we start, for example, in experiment 1 at 26.3 and we end at 21.4 after 6 minutes. And we do the same thing 4 times. So question A is asking, why does the mass decrease during heating? Well, we have to go back and we see that CO2 is being given off, so that gas is being lost, or that gas escapes. So gas is being lost, and that accounts for our decrease in our mass. You could also name the gas. You could say CO2 is being released, or a gas is being given off, a gas is evolved. Any one of those would be acceptable. Now, for stating the colours of the solids, you may not have covered this just yet. Again, depending on the order that your teacher is going through, you would cover this in topic 2C, which would be gases in the atmosphere. But copper carbonate is going to have a green colour, whereas copper oxide is black in colour. So don't worry if you didn't know that just yet. You will know this once you finish all of the course. But of course, in an exam, the expectation is that you have finished the course, so they do sometimes mix in different topics. So which experiment might the decomposition not be complete? Well, let's go back to our results, and we want to compare the last 2 sets of results. So you can see in experiments 2, 3 and 4 it is the same number, whereas in experiment 1 we're still getting a change. So for experiment 1 we're probably still getting some decomposition. So the answer to part C is number 1, and the reason for the choice is that the last 2 masses are different. Remember, we always want to heat to a constant mass. And in the case of our experiment 1, we have not done that. And you can see there is the answers to those past paper questions that, and specifically saying about the fact that the last 2 masses are not the same. So we now have a sample of a CFC, a chlorofluorocarbon, and it contains 0.24 grams of carbon, 0.38 grams of fluorine, and 1.42 grams of chlorine. We want to show by calculation that our empirical formula is CFCl2. So we're going to have our table in order to do this. So we have our element, and we're going to have 3 columns. So we've got our carbon, our fluorine, and our chlorine. So the first thing is the mass. So we have 0.24, 0.38, and 1.42. I then have the atomic masses for each of these, which is 12, 19, and 35.5. When I calculate my number of moles, and remember that would be from our mole triangle, so doing our mass divided by our MR, we would get 0.02, 0.02, and 0.04. Now we want to change that into our whole number ratio, and I've just put WNR for the sake of the space here. So we're going to divide each of them by the smallest number, so 0.02 being our smallest, which would give us a ratio of 1 to 1 to 2, meaning our formula is 1 carbon, 1 fluorine, and 2 chlorines, which is exactly what it says in the question. So this is actually quite a good way to ask this type of question, because if you do not get the empirical formula that they've mentioned in the question, you know you've done something wrong. So it allows you to go back and fix your mistake. Now we know that the relative formula mass of the CFC is 204, and we want to then deduce the molecular formula. So if we have CFCl2, we need to determine the MR for this. So 35.5 times 2 is 71, plus 19 plus 12 gives us an MR of 102 for the empirical formula. To work out the ratio, I do the mass of 204 divided by the empirical mass, which is 102, giving me that ratio of 2. So I now have to do 2 times CFCl2, giving me my molecular formula of C2F2Cl4. I simply just multiply all of the subscripts by that ratio of 2. Now, for the next question, some of the ammonia from the Haber process, which is probably part of another question, is made into fertilizers such as ammonium nitrate. And the equation for this formation is as shown here. So we have NH3 plus HNO3 giving us NH4NO3. And a manufacturer makes a batch of 40 kilograms of ammonium nitrate. Now this question is a calculation from balanced equation. The only difference from what we did previously is this is a structured question. So they've done step 1 for us, giving us the equation. Step 2 is part 1, calculating the moles of the known substance. Step 3 is part 2, the mole ratio, and then calculating the mass of the unknown, step 4, is part 3. So all they've done in this question is, rather than giving you a 5-mark question and ask you to carry it out, they have structured it for you. That's something you can expect at GCSE, to have structured calculations like this. When you go into A-level, they would be more likely to be unstructured. So firstly, we want to calculate the number of moles of our substance. So our MR of our NH4NO3, you would need to work out, and that would give you a total of 80. And one thing that we need to be aware of is watch the units. This is in kilograms, and our MRs are all in grams. So we need to make sure that we convert it. So to work out our number of moles, it's the mass over the MR, because remember we have mass, moles, MR. So I have 40 times 1,000 to convert it into grams, divided by 80 to give me an answer of 500 moles. Then we want to deduce the amount in moles of ammonia. So this is looking at the mole ratio. So we can see that the ammonium nitrate is got a coefficient of 1, and so does the ammonia. So they are in a 1-to-1 ratio. Therefore, you have 500 moles of ammonia. Lastly, we want to calculate the mass. Well, we need the MR of ammonia, which we can determine to be 17. So our mass is equal to the number of moles times the MR, which is 500 times 17, giving you an answer of 8,500 grams. But we want to convert it. You can see that they ask it in kilograms, so we get 8.5 kilograms. So this entire question is saying if we have 8.5 kilograms of ammonia, you can make 8.5 kilograms of ammonia will make 40 kilograms of ammonium nitrate. Lastly, we're going to look at some excess and percentage yield calculations. So magnesium chloride can be made by reacting excess magnesium carbonate with dilute hydrochloric acid. So we have MgCO3 and 2HCl. In one experiment, a sample of 0.05 moles MgCO3 is added to 0.08 of HCl. We want to show by calculation that the MgCO3 is in excess. So if we have MgCO3 and HCl, and we want to draw a table, hopefully we can fit it in, we have our ratio is 1 to 2. I have, this time we don't need to calculate it, I have 0.05 versus 0.08. For my need, if I wanted to use all of the 0.05, I would need twice the amount of that for HCl, which is 0.1. The fact that 0.1 is larger than 0.08, that means that I do not have enough HCl, meaning the MgCO3 is in excess. Now remember, if I had worked this out and my need for HCl was less than 0.08, then the HCl would be in excess. So we just always have to compare the have and the need to each other. Now, in another experiment, 0.05 moles of magnesium carbonate reacts with excess hydrochloric acid. So this is completely separate from part A. A yield of 5.5 grams of the magnesium chloride salt is obtained. We want to calculate the percentage yield. So we need to figure out, first of all, the MR of our MgCl2 6H2O. And when you do that calculation, you can determine that you have an MR of 203. Now, we can see that we have 0.05 moles of the MgCO3, and when you compare that to the salt, they are in a 1-to-1 ratio. So that tells me that I have 0.05 moles of the salt. So my theoretical is going to be 0.05 times 203. This gives me an answer of 10.15 grams. So my percentage yield is the actual over the theoretical. So 5.5 is my actual divided by 10.15 as my theoretical times 100, and I get a percentage yield of 54%. And again, 2 marks, 1 mark for working out your theoretical, 1 mark for working out your percentage yield. And there's the mark scheme for these questions if you have been trying them. As with part 1 of this topic, I would strongly advise that you go through and you practice each of the different types of calculation. So you have your reacting masses, percentage yield, empirical formula, and your excess calculations. Your teacher will be able to provide you with lots of different examples, or you can use the examples in the textbook or check on the internet. There is loads and loads, and genuinely for this topic, practice really does make perfect. If you do have any questions, please feel free to leave a comment below, and we hope to see you back on the channel soon.